fault, and it's been infilled by the groundwater, but on a very different scale, we have a very small fracture here, which may be only millimetres open, and we have a very slight trickle, so very two contrasting fluid thresholds. So, fluid flow through the crust. Okay, many of you think of it as magma, but there's other different fluids, crustal fluids. We have hydrocarbons, for example, and we have water as well, so it's applicable to hydrocarbons. So theoretical results for fluid flow through openings with ideal geometries. We tend to assume that these are an elliptical geometry where they have smooth walls. However, we know this isn't true. They tend to have an irregular wall. Okay, so this is why it's theoretical. Here comes the fun bit of math. This is all taking into account that we have an elliptical fracture with smooth walls. Okay, so here we have a schematic illustration. This rectangular block, and we have fluid flow coming from this end this way, which is represented by Q. Okay, Q is the volumetric flow rate. So we have this beautiful equation, which describes that the volumetric flow rate, which has a unit of cubic meters per second, is the pressure difference. So the pressure difference between where the fluid started and ended. And then we have the cube of the aperture here. So how big is this? So this distance here. This is divided by 12 and the dynamic viscosity. So that's how well will the fluid flow. So it's due to friction. And then you have the width of the plate, so the width of this rectangular block here, divided by the length of the entire sample you're measuring. So this can be rewritten, and the equation is valid for any parallel smooth wall fracture, independent of its orientation, so independent of which way it strikes, whether it's vertical, whether it's horizontal. But we must assume that the host rock is rigid. Okay, so therefore Young's modulus E is infinite. So this equation here, it's a simple one, but it doesn't take into the account of buoyancy, and buoyancy has a large effect, which I'll go through to show you later. So again, we can simplify the equation from before, and we have the volumetric flow rate is equal to the density of the water times the constant of gravity times the fracture width, which is perpendicular to the flow direction. So if you're flowing this way, the width is this way. Okay. Then you've got it times the cube of the aperture of the fracture, even if it is open or closed, divided by the dynamic viscosity times 12. And I here is the hydraulic gradient, and it's defined by this here. Okay? So, Darcy's law, I think you've all heard of Darcy's law. It describes flow through a porous medium, not through fractures, through pores. Okay? And in simple terms, what we have here, Q is equal to a constant times the cross-sectional area in which that flow is travelling through. But we all know, we can apply this into sediments, they've all got pores, but if you were to put this into a fractured medium, for example, I'm looking at sills. Sills have fractures. These fractures are columnar joints, and they're also post-tectonic joints, shear fractures and tension fractures. Then I'm looking at something here called the cubic law, which is the flow rate is equal to a constant times the aperture cubed. So therefore, the cubic law, in simple terms, states that the volumetric flow rate is proportional to the cube of the aperture. And we can make this even more complicated for straight flow or for radial flow. So straight flow is defined here. So we have the density of the water. This can be any fluid. We could have density of oil, for example, times gravity, times dynamic viscosity, and then again the parameters in which that flow is travelling through. Okay, the width and the length. However, when you have radial flow, you must take into account, we're now So this is when you have the pi function coming and the radius of the circle. You all know how to calculate the circumference and the area of a circle. How do you calculate the area of a circle? And the circumference? 2 pi. So this is where this is. Okay? So, from my own research, when I was a master's student, I looked at Lackey, which erupted in 1783. Lackey is a fissure here, and it's 27 kilometres long, extending from the southwest up to the glacier where Grimsby lies. And this fissure has 10 segments. 10 segments representing different stages of the eruption. The important part I want to talk about here, to relate it to fluid flow, is the crater cones. These are the crater cones. Okay, they have different sizes. These ones are quite large, but we have some smaller ones here, and we have a lot of large ones here. Okay, so I measured 140 crater cones, and I plotted them on a cumulative frequency plot. And here we see that we have a really nice exponential. And to justify this, I plotted it as a log block plot, and we have this really nice straight line with a dogtail. Okay, and these have very high correlations. We've got 0.98 here, 0.89 here. So the data fits really nicely. It's all well and good putting it on the graph, but what am I trying to show you here? The point here is looking at this power law distribution and what are the mechanics behind it. And the two mechanics are the cubic law, which I just explained to you. So this says that the large apertures, so these apertures down here, for example these ones here, these are the ones that dominate the fluid flow. This is where most of the magma would have been erupted from, in comparison to these smaller ones. However, these larger ones, we only have a few of these larger apertures and a lot more small apertures. Okay? So this then relates to flow channeling. And the flow channeling is saying that the flow is directed towards the larger apertures, although they may be few, and they contribute a significant effect to this eruption. Okay. Another part of my research is to have a look at hydraulic conductivity. So, for example, we have our sill, and it has lots and lots of fractures, which I'll come to show you later on. But if I wanted to see how that sill has the potential to act as a reservoir for water, groundwater, or a reservoir for hydrocarbons, I want to know how permeable that sill is, or what's its porosity, and this is where the hydraulic conductivity comes into play. So this is the hydraulic conductivity here, represented by K, and this is equal to the density of water, or whatever fluid you're looking at. So the density of water is 1,000 kilograms. Then we have that multiplied by the gravitational constant, 9.81, times the square of the aperture of the fracture. Okay, and then we divide that again by the dynamic viscosity. How easy was that fluid able to flow through the system? So before I talked to you about the cubic law, that the buoyancy effect was not taken into account. However, this does have a significant effect on the results. And this is represented here by this equation. So this is, for example, a fissure, but just like Lackey. So we would have like, this one could be the region of the dike. Okay? The equation here surmises that the aperture of the fracture, so the aperture of the fracture here, okay, we cube that aperture, and then times it by the width of the perpendicular flow. So it flows this way, the width here. The dynamic fluid viscosity of the fluid, for water, that's 1.5 times 10 to the minus 3. And then we have here in brackets the density of the fluid. fluid, so for water that's 1,000, that's a nice easy figure to remember, times the gravitational constant, and then minus this hydraulic gradient. So, and that has to be in the direction of the flow. Okay, so for this one it will be vertical. So still thinking about buoyancy, why is buoyancy important in these equations? Think of a magma rising through the crust. Okay, there are all different mechanical interactions playing a part on that crust. So if we look at a dike, for example, if we've got the dike propagating up through the crust, for example, here, okay, its overpressure must be large enough to overcome the tensile strength of the overlying crust, the overburden. Okay, so here the equation takes the density of the rock now. This is where buoyancy is coming into play. Okay, so I think you should know roughly the density of basalt. What's roughly the density of basalt? Anybody? 2,500, 2,600, that's fine. So we have the density of the rock here minus the density of the fluid, and that's the main difference within this equation. Okay, if we wanted to have a look at something that had now some sort of dip to it and had an angle, it wasn't vertical, then this sine alpha term comes into play. So for example, if you want to look at fluid flow along a fault, okay? So, summarising the cubic law. From looking at the plot that I showed you from Lucky, we know that the largest apertures are the one that dominate the fluid flow. These tend to follow a power law distribution. Okay, power law distributions have that straight line on a log-log plot, but sometimes they may follow a log-normal law, which looks something like. So if our log-log plot looked like this, okay, and on a cumulative frequency plot, it looks like this. Okay, for a log-normal distribution, we'd have something that look like this. It's kind of a power law in disguise, because sometimes this part here can lead to bias. So for example, if I was in the field and I was measuring all my fractures, and I know this happened because I've got plots to show you later, my measuring equipment only goes down to a certain scale. Mine went down to 0.05 millimeters. So any fracture that was smaller than that I wasn't able to measure, and therefore that's where the bias term comes into it. Okay? The other main point of the cubic law is that we're assuming that the plates are smooth. But I'm sure if you ever went over to just looking at the opening slides, the plates weren't completely smooth. There was some irregularity to them. So, therefore, that's going to induce an effect on hydraulic conductivity. So this is the same image that I gave you, but now it's in the snow. It's always nice to have a contrasting picture. And this is now going to summarise what I was trying to talk to you about flow channeling. Okay, so flow channeling is going to take the path of the least resistance. I'm sure if you were walking to university, you take the direct route, you wouldn't walk all the way around the house. It's going to take you too much energy and it's not efficient. Okay, so it's going to take the path of least resistance. So we have different scales. If you remember from that first opening slide, we had the slide where we had water trickling through a very, very small fracture, and then you had the other one, which was the tension fracture with the groundwater running through it. You have other things, waterfalls, for example. Okay, so here we're looking at, this one just takes into account magma, and we're just going to apply it to Lappy. Okay, so fissures, they tend to erupt like a fire fountain, okay, and that would assume that this is all regular, and therefore the volumetric flow rate would be equal, and therefore if it's equal, we're assuming that the plates are smooth. You know this isn't true. Okay, we get something like this. Okay, the flow along parts of the fracture, some of the fissure segments could be wider than other parts. This would channel the magma more efficiently towards the surface. So we have these two centres here. And then in C, we have the fissure cones that we see. These are the scoriae cones or the spatter cones. Just depend on the magma. We'll learn about more in volcanology. And this is what we see along the fissure today. Does that all make sense? Does anybody have any questions? Okay. Because we're going to have a lovely example. So I thought it would be nice if we could try and work through it together, because I've put a lot of equations on the board, and I think it's important that you understand the concept first. So if we go through it together, and then you're going to do an example for yourself. So the example is a hydrofracture in a fault zone, like my sills. Transport water to the surface of the zone. The fracture consists of interconnected segments with a total height of 1,500 metres. The width of the fracture perpendicular to flow is 50 centimetres. The aperture of the fracture is 0.1 centimetres, okay, just an average. The dynamic viscosity of the water here is going to be 5.5 times 10 to the minus 4. And this is, the value I gave you was for water at 5 degrees Celsius. This is much hotter. And its density is 990 kilograms per metre cubed, okay? We are going to assume the vertical network segments of fractures that transport water to originate in a water sill at 1,500 metres depth, and that the host rock of which has a tensile strength of 3 megapascals. Okay, so I'm just going to give you a couple of minutes to mull over the question to make sure you get all the bits of information, because then I'm going to put the overhead projector on and we'll work through it. Okay, so the first part of the question asked, what was the volumetric flow rate determined by the symbol Q when the host rock is rigid? So if the host rock is rigid, are we going to take into the account the effects of buoyancy? The host rock is rigid. Young's modulus is assumed to be infinite. Are we going to take into the effects of buoyancy? No. Okay, so the equation that we're going to use is one from earlier on. Can everyone see this? Okay, so we have Q is equal to the aperture cubed, okay, times the width perpendicular to the flow over the dynamic viscosity. Okay, and then we're not taking into effect buoyancy, so it's just the density of the fluid. So here it's my density F, which is times the gravitational constant minus the pressure gradient. Okay, so that's going to be delta rho over this rock over delta depth. Okay? So, now that it's all put neatly forward on an equation, it seems to me, the way I've laid it out, it's fairly straightforward. Okay, so B cubed, B is the aperture of the fracture, and they said that the aperture of the fracture was 0.1, and we can cube that. However, the aperture was in centimetres, so if we have 0.1 centimetres, does anyone know what that is in metres? 0.1 centimetres is how many metres?
0.001.
Okay. Times the width perpendicular to flow, so this what is here, 50 centimetres, so that's 0.5 metres. 12 times the dynamic viscosity. The dynamic viscosity of the water at 50 degrees was 5.5 times 10 to the minus 4. Does that part so far make sense? You know where all the figures are coming from, and you know why it's important to use the correct units, why we're not using centimetres, we're using metres. Okay. The density of the fluid, the density of the water is 990 kilograms per metre cubed. So it's 990 multiplied by the gravitational constant 9.81. Okay. Minus the pressure gradient. Now, we were told that the tensile strength of the rock was 3 megapascals, so that's 3 times 10 to the 6. And we know that the depth was 1,500 meters, so divided by 1,500. Okay, so Q is equal to, I don't have a calculator, so I think you can work out the last part and then let me know what answers you get. Actually, I've made this more. The major point here is that the hydrogen gradient always goes from high to low. So therefore, it will be minus, and a minus makes a plus. Okay, so it will be, see this part here will become a plus.
Can you explain the last time again, the pressure gradient?
The pressure gradient?
Yeah, I don't get that.
So it would go from a high pressure, for example, 6 pascals, and then the outlet would be at a very low, even 0 pascals. So therefore, the gradient is negative. And we already have in this equation here, you see there's already a negative sign.
Yeah.
And then we have a negative gradient, so we have 2 negatives that make a positive. negative.
So what is that? Delta PE? Is that rho of what? I can't see it
No,
clearly.
it's the tensile strength of the host rock. That's
So
not a rho, that's meant to be
pressure.
Okay.
PE.
Tensile. So the first one is the tensile stress of the rock
tensile strength of the rock. Yeah.
divided by.
Divided by the depth, which was 50
So have you seen the volumetric flow rate value? Does that seem familiar? He's lost it. I get pressure gradient. He's like,
None of the symbols make sense.
that only pressure gradient one is still good.
So why is it delta PE? Delta means change. That's the definition of delta.
That, yeah.
Yeah. So that's symbol before yellow means change for what? So there's the change.
Why isn't it a word delta?
I don't know. It's not capitalized. It shows like the change in tensile strength over the change in depth. Is it 40 minutes in? Actually, it is.
Exactly 8.8 times 10 to the minus 4.
Yeah, that's fine. So we've got a reasonable answer over here. 8.8 times 10 to the minus 4. Does everyone agree with that? Has anyone else got the same or not got the same? Yeah, okay.
So go to go up a little bit. It says PW. Do you see that?
Okay.
It is PW. Behind. Because we don't have time when we're later. So this M stands for nothing. So what time is not any it's a sedimentary basis.
Does that all make sense? That equation, how to use it? Okay, so the tensile strength, which was the question that I was, is equal to the PE. Okay. Right. So the second part of the question is asking now, when the host rock is elastic and has a density of 2,500, what term are we going to take into effect?
Buoyancy.
Buoyancy. Okay. So the equation that you will want to use is this one. Okay. The top equation. So I think you need to do that one on your own.
What does P stand for?
So it's just different value, a different symbol.
Why would you do that? Density of the water is rho W. So the delta. Oh, come on, man. You're using these equations in exam. What if you go in, you know how to use it, but you don't understand the terms, which is like P is P. Exactly, that's it. Done. You might as well walk out the exam.
Syntax error.
Walk out.
thought I'd be smart. I thought I'd be missing. Okay, I'll be smart. I'll just plug it in the same way because it's nothing different. Yeah, we know the reference to she gave it to us. 2,500. Yeah, that's 2,500. Minus PW is 990. So yeah, that's probably different things. What's that? You still like the show? Probably 2 or 1. Ask them. Oh, that's what it's in brackets. I've done my thing. Or paid attention to maths GCSE. What I wanted to. No, I was pretty recent. It's just because I didn't do anything. I just forgot it. I need to do stuff. Did you do it? Yeah. End of this week.
Does anyone have an answer? What did you get?
Oh no, I definitely didn't get that.
What did you get?
Oh, I got a massive number. 9.7 times 10,000. I just put something in the wrong place.
Okay. Take the answer away.
Me? I haven't even got the message. Okay, that's fine.
That's enough. I think I saw the shit that you didn't have a calculator.
Everything was great until 18 months.
Oh yeah, that's true actually. 18 months.
I was a genius at that point. After that, I was like, what was it?
82 as in the second year.
Yeah, that's right.
As long as you work through that as well. You're less motivated and you don't know what to do. So in fact, if you don't understand it, don't teach this thing. There's no chance you're going to understand it.
Any advances on 9?
I got 1.27 post 10.
No, it's really annoying. What? No, no, it's not when I was younger, that's the I don't know if it's like the elements really, or the bit, or the yeah, I've got
Does anyone else agree with Hannah's figure? Yeah? Okay, so can you all see the difference that buoyancy has on the results? Okay, so buoyancy is the ability that with the host rock being able to act elastically. Okay, so we've got a difference here. Albus nicely calculated for us at 1.48. Okay, so there's a vast difference when you take into effect the buoyancy, and I think it's really important. Okay, so I thought I'd brighten up your morning with a bit of my stuff after we go through the principles of why I did it. Okay, so fluid flow through fracture sets. So now we have more than one fracture. Okay, so we have two fractures with the hydraulic gradient being vertical, with the highest pressure down here and the outlet pressure being at the top. So when we go in the field, nothing is as equal as this. We have different apertures, so we can you need to summate all your apertures, okay, to get an average. and we can do some more math. And this is taking into account parallel flow. Here we assume that the aperture is equal, so all the apertures, there's no variation. It's quite rare that you're going to find this. And they strike parallel to the direction of flow. So strike parallel to the direction of flow. So flow is coming in through the board, okay? So they're striking that direction too, okay? And we have all the same parameters as before, but the two different parameters are m and the uppercase M, and this is taking into effect now that we have more than one fracture, so we're looking at the thickness of the layer. So this is the uppercase M, and we're looking at the number of fractures. So basically, the number of fractures within this given section. So when I'm in the field, for example, I take a profile line of 10 meters, 20 meters, and I measure all the fractures for several hours, and then I'm going to show you what my results were. So this is my fieldwork at the Windsill. This is northeast England, and you can see here that there are some really beautiful concrete joints. Okay, these are all these vertical joints. Okay, and I sat down and I had 3 scan lines. Me and John, I did 3 scan lines, and there were several main features that we were trying to measure. These are the orientation of the fractures. So which way was the fracture striking? We've got our compass primes. Where is the fracture intersecting on my profile? So you've got the fracture in outcrop, you've got your profile line on the floor. Where does that meet that profile line? Okay? It'll all become clear later. The aperture of the fractures. Were they open? Were they closed? Were they infilled with secondary minerals like quartz or calcite? Because if they're infilled, then they're going to be a barrier to fluid flow. Okay, then it's not going to be a conduit like the open fractures. Then I was able to measure the fracture spacing. So that's the distance between two fractures. So if I have one fracture here, one fracture here, what is the distance between these two pens? Okay, this is the fracture spacing for 2 vertical fractures, same is apparent for horizontal fractures. And then fracture frequency is how many fractures were in a given area. So I took a 1 meter squared area and then I counted all the fractures within that transect. And then I was able to do lots of plots. And then I'm going to talk to you about these plots in respect to how the fractures become interconnected. It's all, you can have fluid flow through one fracture, but it's not very good if you're looking for oil, for example. You want it to be in a vast area. So you need the fractures to become interconnected with one another. Okay? Then we'll have a look how my results, we use them to calculate permeabilities and porosities, and then that can help with storage capacities. So, I got back and I decided that it would be really fun to do this on coral, though it wasn't after 4 hours. So this is an example from the Windsill. This is actually off of one of the islands just off the coast. And can you see that there's really dense fracturing? This is only 20 centimetres. We've got fracture clustering, so we've got many fractures here, sparser fractures here, for example. Okay? So generally, from what I measured in the field, this is what I was able to plot. So this is a Rose diagram of all the vertical fractures, and you can see there are 2 main trends, this trend here and this trend here. So you've got 2 sorts of sub-vertical fractures that can cross-cut each other, if they will. Okay? Then we've got the horizontal fractures, and they're striking mainly in the northeast-southwest direction with a small clustering in this direction. Okay, so if we have these, we know that we can start to interconnect the fractures, but this is only taking into account their strike. Okay, how about what angle did they dip at? Because if you had 2 fractures like this, they may as well be parallel to each other, but if they start to dip, they can start to intersect with each other. So this is where we can classify the vertical fractures. Most of them range between 45 and 90 degrees, and the horizontal fractures, which range between 0 and 40 degrees. Okay? Here are some plots, and from what I told you over here, what kind of distribution am I seeing on my graphs? Is it a log normal distribution, or is it a parallel distribution?
Power law.
Why is it a parallel? And not a log normal distribution?
Because it's the ones that go once.
Yeah, just look at the shape. Just look at the shape of the histogram. Does it start from the top and go nicely down, which it does here, but there's a blip here? Okay, these are log normal distributions, okay? They go up and come back down. Okay? So, the first two top plots, these are fracture spacing, so the distance between two sets of fractures, and they display similar patterns. Then I was able to plot the fracture frequency, and can you see that broadly they are the same pattern, okay? So 2D fracture sets, we have this curve, and in 1D we have this curve similar to what we see here. We've got a small amount of fractures within a small area, and then we've got this peak here around 4 or 5 fracture frequency per meter, so 4 or 5 fractures within that transect. So here we're starting to see how the fractures interconnect. So the fracture frequency is really important because we're not looking at it in 1D space, so just along the transect line, we're looking at it too in 2D, so in that area, in that transect area. And you can see broadly as the area increases, we can count more and more fractures, especially in this tail part of the plot. And if I was to do this for 3D, you'd have even a longer tail. Okay? So, I then plotted all my fracture aperture data, and we have this really nice power law distribution, okay? Can you see that there are many small fractures, for example here, down here, we have a really strong correlation. This is 0.98, so it's almost perfect, not quite. We have these large apertures that dominate the fluid flow, okay? So, any sort of crustal fluids that are going to be transported into the cell, they will reside within these large fractures. So, here's another fracture map that I decided to do. This one took me a couple of days. And I decided it would be really fun to put it into a numerical modelling program, COMSOL, and put it in a time-dependent frame. And I'm going to show you the results that originally took me nearly 3 weeks to get out before I sorted it out. So here's the fracture map. This is a coastal section, so all the fractures are in yellow. This is just a 12-metre high section, and this is the stationary model. So any the highest velocity that you're going to see, it's really small, okay, 0.006 metres per second. And I'm just going to show you here a model for water. I've done it with oil, and it's a lot slower. Okay, so I thought I'd play you a movie. Like it works. There we go. Okay, so can you see that the flow is dominated along the vertical fractures first? It's already near the top here, and then it starts to transect along the horizontal ones. So generally, the higher velocities are along these vertical, subvertical fractures. Okay, the pressure gradient is in this direction again. Go back. The pressure gradient is in this direction, so I had an outlet pressure of 0 and inlet pressure of 6 pascals. So these are the results. So to summarise this. There are 2 main classes of fractures from my Rose diagrams and the histogram plot associated with it. We have subvertical fractures and subhorizontal fractures, and it's the interconnectivity of these fractures that are really important, because without this interconnectivity, for all these intersections travel in one direction and not throughout the system. That's a really important factor that you need to consider. I was able to calculate all the permeability and porosity of these fracture systems from all the profiles that I took. And from this I was able to demonstrate if it was going to be a good reservoir, and in general the conclusion was it was, because we had highly interconnected fractures. We've seen that on the fracture spacing plots and the fracture frequency plots. Okay, they all interconnect, and you can see it visually on plots like this. Okay, the fracture spacing and fracture frequency plots, they followed a log normal distribution. They again give us implications for the permeability and the porosities. And most of all, which is important to this lecture, is that the flow is channeled along fractures with the largest aperture. So you saw that on my log plot of the aperture, on a plot like this. These larger fractures are going to dominate the flow in comparison to these numerous small apertures. Okay, and the flow, therefore, this we can relate it again to flow channeling. It's not just in magmatic studies. We can relate this to flow channeling, saying that the flow dominates along the vertical, the subvertical fractures in which you saw in the animation there. Okay, I think I'm going to give it a rest. I think there's a
Okay, fine. So we take then a break now. We'll get a coffee, wake up, and so on. And